My name is Enrico. I'm a tech lead in the data streams team at Yelp. Data stream is the team that builds and maintains the overall streaming infrastructure and data pipeline of Yelp. It's actually a large team. There are 3 teams within data streams. We go from maintaining the lower level Kafka infrastructure, libraries that we use to write, to produce and consume from Kafka, schema registry, schematization, and then also the Flink deployment and Flink infrastructure, some generalizable Flink infrastructure, kind of something we consider infrastructure Flink applications, and then the entire connector ecosystem. So that's the team, the data streams team is responsible for all of this. Today, I'm going to talk about one of these generalizable applications. It's called Stream SQL, and it's a service built around the Flink SQL API of Flink. So before we start, let's look at how streaming fits into the Yelp mission. Our mission is to connect people with great local businesses. And to do that, we provide a number of features. You can look up places on Yelp, maybe the favorite and best coffee shop in the area. You can look at what are the recommended dishes in a restaurant, add yourself to the wait list, and so on. All these features, what they're trying to do is create connections between users and businesses. And obviously, the faster we can create these connections and the more accurate these connections are, the better value we provide to both users, that are people using Yelp, and businesses that are our customers. So in this sense, over the past probably 5 to 6 years, we have been shifting our data processing from the batch-oriented world, where it will take hours or days to get results, to a more real-time oriented world where the latency will be of seconds or minutes, and we will use what we could consider maybe today kind of more modern technology, things like Kafka, Flink, Beam, and so on. Today, our streaming infrastructure is actually powering most of kind of Yelp core business. So we have a variety of use cases and applications built on top of our data pipeline. We go from notifications with real-time visit detections. Our entire indexing pipeline, user search, is built, leverages our streaming infrastructure. Some transaction flows. We use streaming for machine learning features because we generate some features in real time. And also the ones that we generate offline, they are typically ingested back into our data pipeline so they can leverage the connector ecosystem to then store the same data into maybe Cassandra for online prediction, or data lake for training over historical data. And then like our product development itself is actually based on the streaming infrastructure because that's how we extract metrics and gather the metrics to evaluate experiments. Over the past few years, we have been kind of evolving the infrastructure itself, introducing new technologies. And what we observed is obviously over time, every time we were introducing a new tool, more powerful tool, our data, the data produced into the streaming infrastructure has been growing almost exponentially. So for example, when we introduced Flink, we saw we unlocked so many different use cases that actually allowed our users, internal users that are other developers, to build more complicated applications. So we introduced Flink in 2017, early 2017, so we've been running Flink for about 2.5 years now. What really Flink did for us was unlocking real-time data processing at scale. And it came with a number actually of interesting features. Like first of all, stateful processing and then event time processing. It's really critical when you do stream processing. And then we got kind of really rich streaming-oriented API. If you've used the Flink before, you probably used the data stream API. And the value that we got from the data stream API was really abstracting away what were the lower level details of the streaming infrastructure. Things like what Kafka clusters you are consuming from, what Kafka cluster you are producing to. For a developer building a Flink application, they pretty much just need to interact with the data stream API and focus on the business logic. So all of these things we got when we introduced Flink in 2017. Thanks to Flink, we implemented a number of what we call modules. And this kind of go side by side with also custom applications that developers can build natively using the Flink API. But these are what we consider infrastructure applications. So we have all of our connector ecosystem, connects that can source data from Cassandra or MySQL and ingest that into Cassandra, Elasticsearch, Redshift, and so on. We have the component we'll look into details today called Stream SQL. And then other components like joiner, aggregator, sessionizer. Those are all components that are specialized in a specific job, and they will consume data from Kafka, do the processing that they are specialized to do, and then write back into Kafka. And all these components, they can be connected together by using Kafka topics. So if you look at the end result, we end up with a data pipeline stack that looks like this, where we have on the right all of our data sources. Could be MySQL, Cassandra, so data stores, or even web services, events, even like Spark batch jobs. And then we have this central stage, that is the stage that is doing all the processing. And we connect all these different components using Kafka topics. And then we have our data sinks, where we ingest that in data stores. And all of this is controlled by this thing called the schematizer, that is a sort of a control plan, or pretty much a kind of more powerful schema registry. But let's focus on SQL. I'm sure you have seen probably other talks in this Flink Forward. There's been a lot of talking about SQL. And if you look at the industry trend today, there is a SQL interface is being introduced to really many different data sources. And as a consequence, data processing systems, you see like Flink, Kafka, Streams, Spark, they are all providing a SQL interface for doing processing. And the reason is that SQL is an extremely popular language for data scientists, data analysts, and also for developers. So what we are kind of looking into, the reason why we are looking into SQL, at least at Yelp, is because we know that stream processing may actually be complicated, and there is a certain barrier of entry to kind of get adjusted, especially when developers are coming from a batch-oriented world, to get adjusted to the streaming world. By introducing SQL, we hope to decrease that barrier of entry and give a tool that developers, an interface that developers are at least kind of familiar with, and something that they can also iterate very quickly on. So if we focus on the Flink side, if I look at the documentation that is coming from the documentation, is the different API abstractions provided by Flink. The highest level abstraction is the SQL. And it's implemented in Flink natively. You get this SQL parser that allows you to define Flink jobs using SQL. It's based on Apache Calcite. It's this framework to sort of build databases. It comes with a query parser, converts your query into your SQL parser. A SQL parser converts a query into a logical plan. And then what Flink implements is a driver that will convert the logical plan into different operators that will actually execute the query. It supports both batch and streaming. What we care about mostly at Yelp is the streaming side of SQL. So we actually don't use SQL currently for batch on Flink. All of the nice thing that we see in Flink is that we can actually mix and match all these different API level of abstraction that you see there. So you can start from a data stream, do some transformation, and then register that stream into the table API and have a SQL query running on top of that, and then going back into the data stream. The center of the system is this table environment, which is a wrapper around, so it looks like a wrapper around the stream execution environment. If you have used Flink, you're probably familiar with that. It allows you to interact with the SQL engine in Flink, so we have things like register a table, parse and translate SQL, register UDFs and stuff like that. Now, if you're probably trying to use Flink SQL today and you already have Avro data or I think there is already compatibility, so you can probably just register your stream using the table API, and I believe Flink will be able to automatically detect the proper schema, and you should be able to, you should be ready to go and basically write your SQL query and see the result. At Yelp, we have a little bit of a complex data structure that we use when we, that are kind of what represents our messages flowing through Kafka. So we actually had to customize the table source to be able to adapt and translate our data type to what Flink would expect. If you have a similar situation, doing that is actually not terribly complicated. You need to extend this class called stream table source. And then one thing that you want to implement is making sure that you're implementing the extraction of the processing time or event time. At Yelp, we actually, in our class, the way we extended it, we actually extract both, so that then the user at query time can decide whether they want to use processing time or row time or event time characteristic. And then the other thing that your custom table source will do is basically get a data stream of type row, and that's the type that Flink knows how to manipulate in the when running a SQL query. And then the table schema. What you're actually, what you end up doing is basically creating this sort of two layers of translation. The first layer of translation is your schema. So if you have your schema in input, you have this translation module. Let's assume that your schema is in Avro, even if again, that's probably supported natively in Flink. So you have this converter. This converter will take your schema, convert into a table schema, where a table schema is just the columns, the name of the columns, and the type of the columns in the table that is represented inside Flink. And then you have SQL. It will perform some transformation and give us a result of the query, a new table with maybe different columns. It really depends on what kind of transformation you're doing. And then you have on the other side, so that is the schema side. On the other side, you also need to convert and kind of serialize the data that is flowing through your system, so that you are going from, maybe you have an Avro record, and you're going from the Avro record into a row. And then SQL will transform that row that is in input and probably emit another row in output. So you actually, what we do at Yelp, I was saying that all these modules are connected through Kafka topics. So we actually read from Kafka, we do this translation, we execute the query, and then we actually go back into a record that we can ingest back into Kafka. So we extract a table schema from an Avro, and then after we apply the transformation, we extract an Avro schema from a table schema. And same goes for the record, where we go from a row to a record. When you write your output, things to keep in mind are how your output is going to be written in the data stream and probably also in Kafka. It really depends on your query. Typically, most queries use what's called an append stream. And that's because the output is, every time it's processing elements, let's say you're doing a filter or a projection. In those cases, usually the output is simply a new record that can be appended to what was the stream in output. However, there are some queries, like maybe on a window group by, where you actually need to update a result that was provided previously. So imagine doing a count and a group by over a specific key. At a certain point in time, because this is a stream, the value is 10. Now you receive another element, and the value is 11. So what Flink needs to be able to do is to update the previous value from 10 to 11. And the way it's done in Flink is by using retraction. And that retraction is just a way to represent updates. It's a delete followed by a create or an insert. And it's internally implemented with a data stream where there is a Boolean value represents a delete or an insert. The way we expose all of this to users is through a config file. So we have this YAML file here. Users can specify input streams. They can specify more than one, because if they are doing a join, that's how they do it. And then there is ownership information. We know who is running a specific query, and then the body of the query itself. We allow, as I mentioned earlier, users to specify the time characteristic, so they can use processing time or event time, and they will adjust to kind of configure Flink properly. Parallelism, and then finally the output stream. There's this element here, event time column. It's actually really important, because when you are implementing something in streaming, there is always one important component is the notion of time. So this event time column allows our users to specify what field in the output they want to use as event time. And that's because we store event timestamp in a standard field across all the messages that are flowing through the data pipeline. So let's say that they're doing windowing, they'll probably have a window start or a window end, and they'll tell us that that is the column that they want to use as event time in the output. Their interface is complemented by tooling. So they have tooling to run, to execute queries in dry run, and then we have a tool that will automatically generate the output schema of a query. Now, we do not automatically register the output schema, and that's because there's some information of the schema that we can't automatically extract, and that information is usually documentation. So let's say you are introducing a new field. If you are using fields, you're just maybe creating a projection or using some of the fields of the input schema, then the tool tries to be smart and reuse the same documentation. But what if you are creating a new field? In that case, we've pretty much forced users, developers, to actually write documentation for that field. Then that doesn't mean that the documentation is going to be good, but at least they are forced to write something. And then they can add user-defined functions, but I won't be going into details in this talk. We also support testing for queries, and the way we do that is by reusing the testing framework that we use for any other Flink application. And it's based on Docker. We have this component here called Yelp Compose, which is just a wrapper around Docker Compose, takes care of some internal Yelp integration. And that component will launch an entire kind of containerized data pipeline configuration. So we'll have a schema registry, we'll have our Kafka cluster, and for simplicity, typically there is one container that contains job manager and task manager. Our test cases are written in Python. So users will say, this is the input data of my query. They will produce the data into Kafka, spin up the job that is running the query, and then read the data, the result of the query from Kafka, and then run any assertion or a conditional statement that is required to validate the test. Currently, this is we released this about 1 year, probably 1 year ago, I'd say, or 1.5 years ago. And over the course of the past 1 year, we had about 40 production queries. The largest query is running about 140,000 messages a second. Some of the use cases that we have, typically we have data preparation before a sync connector that involves some projection, filtering. We have a deduping of events, usually over short windows, and we do that because maybe after the query, we are using that data to call some external API, and deduping in that case makes sense because we are saving on a request that we are sending maybe to an external vendor. And then also we have some use cases of window aggregation using some specialized UDFs. In terms of current limitations, we have it's the first one, kind of future improvements really. The first one is adding support for upsert stream into the table source. What that means is that if you have a stream representing a table changelog, so a stream that is a sequence of create, updates, and delete, by having this functionality in Flink, we will be able to materialize the table as it's being updated into the Flink SQL itself, and then run some more complex queries, things like unwindowed joins, for example. The second ticket is actually something that is preventing us from upgrading to a newer version as compared to 1.6. We tried to upgrade, and there's this issue that doesn't spread out the tasks heavily across task managers. And because we run multi-tenant clusters, this is basically causing us to fall behind in some queries and basically not optimal use of resources. And that's why we are right now stuck on 1.6. That will be hopefully fixed in 1.10, so we'll be upgrading to 1.10 directly in that case. And then some other interesting things, for example, tunable window firing strategies. One use case that we have is that we have 24-hour windows, but we want to know the result of the query as soon as it gets updated. Let's say a group by account over a 24-hour window. We want to keep seeing what is the new value of the account. That is something we haven't been able to do easily in Stream SQL, and typically in Flink, you would use maybe a global window with a custom trigger. And then the last one is something that we are looking into internally. As I showed before, we have all these different modules that we are connected through Kafka topics. And we are looking into providing a unified API so that users can get a Stream SQL query connected to a joinery, maybe connected to a connector, all by just using the same unified interface, and hopefully even a UI. I'm not covering deployment, but Antonio covered deployment in an earlier talk today. So if you attended the talk, that's great. Otherwise, you can watch the video, and he goes into much more details around how we deploy Flink at scale. These are our engineering contacts. And this is the end of the talk. Thank you for listening. And I can take any question, probably.
Could you give an idea of how often you're able to solve the majority of your problems with a SQL and a UDF versus having to go straight to code?
Yeah, I don't have good statistics. I would say we always try to use SQL at first, but then there are use cases where maybe you have like a complex windowing. There are like, in most cases, there are just strong limitations in SQL that just don't allow us to use it. And the one about like the 24-hour window of with the update, constant update, is one of them. We couldn't find a good way to do that in SQL, so we said, okay, we need to implement a Flink app. And in general, like when we have a complex session windows, late events, there are features that are simply not supported. So in those cases, we either, now we are introducing Beam, so we'll have a Python API, so in that case, we'll either recommend to use Beam or to use the Flink native API.
Are there any other questions? Thank you very much.
So you just mentioned Beam. Are you adopting Beam primarily for the Python integration?
Yeah, that's correct.
Okay, so thank you very much.
Thank you.